This conference will now be recorded.
Good afternoon, students. Yesterday class, we discussed the steady seepage flow condition in the infinite cohesionless soil stability analysis. So last class, I explained this steady seepage flow condition in the soil slope. This is an important discussion, the steady seepage flow condition, because the steady seepage develops the pore water pressure in the soil. So that is very important concept in soils. By knowing that pore water pressure, we can calculate the effective stress developed in the soil. So I am going to revise that steady seepage condition briefly in the today's class. Then we will discuss the other topics in unit 2. So please everyone focus on this steady seepage condition. Seepage means the flow of water through soil. The soil is a permeable material. Due to that property of permeability, engineering property, the soil allows the flow of water through it. That is called seepage. In the infinite soil slope, during the rainy season, the rainwater enters into the soil and the rainwater starts moving in the infinite soil slope in the downward direction. So check the diagram. In the diagram, we indicated the seepage flow in the infinite cohesionless soil slope. This is the direction of seepage flow. This seepage flow direction is parallel to the infinite cohesionless soil slope AB. The direction of seepage flow parallel to this soil slope AB. Because of this seepage flow, due to this seepage flow, the entire soil in this soil slope is in saturated condition. So that is due to this seepage flow. Now coming to the stability analysis of this particular infinite cohesionless soil slope under this seepage flow condition. Already we discussed two conditions in infinite cohesionless soil slope. One is dry soil condition. Next one is submerged soil condition. For both conditions, I discussed with you the factor of safety equation Fs. So in the dry condition as well as in the submerged condition, we discussed the factor of safety of the infinite oceanless soil slope. Now in this steady seepage condition also, steady seepage means the flow of water is in steady condition. So we are going to discuss in that seepage flow condition, what is the factor of safety equation for this infinite cohesionless soil slope. Now coming to that derivation of factor of safety for this third condition, seepage flow condition. Now to discuss that factor of safety derivation, we consider the infinite cohesionless soil slope AB, making the angle I with the horizontal. We know that the infinite cohesionless soil slope subjected to translational failure. So we consider in this infinite cohesionless soil slope the translational failure plane CD. This failure plane is parallel to soil slope AB because the failure is translational failure. Take H is the vertical height between the soil slope AB and the failure plane CD, and we are in the third condition. In that third condition, we assume that the water is flowing in the soil, that is seepage flow. Because of this water flow, the entire soil is in saturated condition. To discuss the stability analysis of this soil slope AB under this seepage flow condition, consider the soil prism ABCD between the soil slope AB and the failure plane CD. H is the vertical height of the soil prism. B is the inclined width of soil prism. We know that in this soil prism, the horizontal width is B cos I. So the area of this soil prism is H into the horizontal width B cos I. That is the area of this soil prism. Take the unit thickness of this soil prism in the perpendicular direction, take the unit thickness. Then the volume of this soil prism is height h into horizontal width b cos I into the thickness, unit thickness 1. So the volume of this soil prism is h into b cos I. In the seepage flow condition, entire soil is in saturated condition. So in this analysis, in the third case, we must consider the another unit weight of this soil, that is the saturated unit weight of soil. In the first condition, dry condition, we consider the bulk unit weight of soil gamma. In the second condition, submerged condition, we consider the submerged unit weight of soil gamma dash. Whereas in the third condition, seepage flow condition, since this entire soil is in saturated situation, here we consider the another unit weight of soil gamma saturation, that is called the saturated unit weight of soil. That saturated unit weight is equal to gamma saturation, that is equal to weight of this soil prism. W is the weight of the soil prism divided by volume of the soil prism. Volume V is equal to H into B cos I. Now coming to that calculation of the weight of this soil prism first. So first we calculated the horizontal width of the soil prism. The horizontal width is B cos I. So the area of this soil prism is H into B cos I. Take W is the weight of this soil. In the seepage flow condition, the soil is in saturated condition. So here the soil is called the saturated soil. Since the soil is saturated soil, we must consider the unit weight called gamma saturation, the saturated unit weight of soil. So take unit thickness of this particular soil prism. In the perpendicular direction, take the unit thickness, calculate the area of the soil prism first, h into horizontal width b cos I into unit thickness 1 is the volume of the soil prism, hb into cos I. And here gamma saturation is the unit weight of soil. This gamma saturation is equal to weight W divided by volume hb cos I. So the weight of the soil prism W is equal to gamma saturation into H into V cos I. This is the weight W of the soil prism in the seepage flow condition. W is equal to gamma saturation into H into B cos I. We know that on the inclined plane CD, number of times we discuss, on the inclined plane CD, we resolve this weight W. The weight is acting vertically downward. On the inclined plane CD, that is the failure plane. On the plane CD, we can resolve this weight W into two components. One is tangential component T parallel to surface CD. Other one is normal component N perpendicular to surface CD. Please check this weight. The weight is the force, gravitational force. W is the gravitational force, that is the weight of the soil prism. The weight is not the stress. The weight is the gravitational force. So we resolve this weight W into two components. One is the tangential component. It is called tangential force. Other one is the normal component. It is called the normal force N. The tangential force T acting in the downward direction parallel to surface CD. The normal force N acting in downward direction perpendicular to surface CD. We know that this tangential component T or the tangential force T is equal to W cos 90 minus I, W sin I. Then this normal force or the normal component N is equal to W sin 90 minus I, W cos I. So resolve this weight W into the tangential component and the normal component. The tangential component T is W sin I, the normal component N is W cos I. So these are the components. These components are forces because the weight is a gravitational force. Please keep that in mind. The weight is not the stress. weight is the gravitational force. So the tangential component is tangential force. The normal component is normal force. That normal component N is equal to W cos I. We know in the third condition, the weight W is equal to gamma saturation into H into V cos I. This is the weight W into cos I. So this normal force N is equal to gamma saturation into H into B into cos I cos square I. Then the other component is tangential component or the tangential force. T is equal to W sin I. In the third condition, weight W is equal to gamma saturation HB into cos I into sin I. So this tangential component T or the tangential force T is equal to gamma saturation HB into cos I into sin I. So in this third condition, first we calculate the weight of the soil prism in the seepage flow condition. Then we separate that weight into two components, normal component N and the tangential component T. Now coming to the effect of seepage flow in that soil slope. What is the effect of seepage flow in the soil slope? Now look at this direction of seepage flow. The seepage flow acting is in the downward direction. Because of this seepage flow means water flow. Because of this seepage flow, this entire soil, the entire soil in the soil prism subjected to the another stress, not the force please. Because of this seepage flow, the entire soil in the soil prism subjected to the another stress known as the pore water pressure. So please follow this carefully. Because of the seepage flow in the soil, this entire soil in the soil prism subjected to the another stress, not the force. The another stress known as pore water pressure. So whenever, please remember, whenever water is flowing in the soil, so whatever that problem may be, not only in the stability of slopes, whatever that problem may be, whenever the water is flowing in the soil, that flowing water develops additional stress in the soil, that is called the pore water pressure. The pore water pressure is always acting in vertically upward direction. Whether the seepage flow is in the inclined direction or in the horizontal direction or in the vertical direction, whatever the direction of this seepage flow, the pore water pressure in the soil is acting in vertically upward direction. The magnitude of that pore water pressure, we indicate that pore water pressure with the symbol small u. The pore water pressure indicated as small u. That pore water pressure is equal to unit weight of water gamma W into the vertical height of seepage flow. Here, this is the height of the seepage flow perpendicular to the direction of seepage flow. So this is also called the height of the soil prism perpendicular to the direction of seepage flow. So the magnitude of pore water pressure in the soil due to this seepage flow, this entire soil subjected to pore water pressure, that magnitude of pore water pressure in this
काय राय
Dear students, please give me the response. Is my voice audible to you? Due to the network
sir,
problem. Okay, please.
audible, sir.
Sorry for the interruption. It is a network problem. Now coming to this continuation of topic, because of the network problem, the connection was lost. Now coming to this discussion, please check this slide on the cell phones. Check this diagram on the cell phones. Give me the response. Can you see that? Can you see the diagram on the cell phones? Please give me the response.
Yes,
Can you see that diagram on the cell phones?
Yes, sir.
Yes, sir.
Okay. Okay. Now coming to this seepage flow condition, just now we discussed the weight of soil prism W. We resolve that weight W into normal component and also tangential component. Then the next is seepage flow in the soil slope. Check this direction of seepage flow. The seepage flow is parallel to the soil slope. Then this seepage flow, please follow this carefully. Whenever the seepage flow happened in soil, that seepage flow produces additional stress in the soil, that is called pore water pressure. So whenever the seepage flow happened in soil, that seepage flow produces additional stress in the soil, that is called pore water pressure. It is not the force, please. It is pore water pressure. That pore water pressure is always acting in vertically upward direction. Whether the seepage flow is horizontal, seepage flow is vertical, seepage flow is inclined, the pore water pressure in the soil is always acting in vertically upward direction. That magnitude of pore water pressure, we indicate that pore water pressure as small u. The magnitude of that pore water pressure is equal to unit weight of water gamma W into the height of this soil prism perpendicular to direction of seepage flow. So check this height, everyone. This is the height of the soil prism perpendicular to direction of seepage flow. This height is not equal to h. H is the vertical height, whereas this is the height perpendicular to direction of seepage flow, that is h into cos I. Now I will explain how this height is h into cos I. Check this diagram on the cell phones. Follow this next diagram on the cell phones. Check this diagram. We know that in the third condition, the seepage flow is happened in the soil in downward direction. This is the direction of the seepage flow. The seepage flow is parallel to the soil slope. So this seepage flow is making the angle I with horizontal. The direction of seepage flow is making angle I with horizontal. Now check this right angle triangle here, the bottom right angle triangle. Here the angle is I and here the angle is 90 degrees. So this remaining angle is 90 minus I. The sum of three angles is equal to 180. So this remaining angle is 90 minus I. This is the height of the soil prism perpendicular to the direction of seepage flow. This line PS. PS is the height of the soil prism perpendicular to direction of seepage flow. So the line PS with this seepage flow making the angle 90. So these two angles is 90 plus 90 minus I, 180. Here we have semicircle. So this remaining angle is I. So check this angle I carefully. So here the total angle in the semicircle, the total angle is 180. So this remaining angle is I, because 90 minus I plus 90, 180 minus I. So this remaining angle is I. Now take this right angle triangle PSR. Take this right angle triangle PSR with respect to this angle I. Cos I is equal to the side PS divided by the side PR. because cos I is equal to adjacent side by hypotenuse. So cos I is equal to PS divided by PR. PR is equal to H. So this length PS is equal to H cos I. This PS is the height of the soil prism perpendicular to direction of seepage flow. So the height of the soil prism, this height of the soil prism perpendicular to direction of seepage flow is H cos I. Now at this bottom of the soil prism, that is on the surface CD, due to this seepage flow, the pore water pressure acting vertically upward direction. The magnitude of the pore water pressure is equal to gamma W into H cos I. That is the magnitude of pore water pressure acting at the bottom of this soil prism. So this soil prism, check this diagram everyone. This soil prism is under seepage flow condition. This seepage flow produces the pore water pressure on the soil prism. The pore water pressure acting vertically upward direction. The magnitude of that pore water pressure is equal to gamma W, unit weight of water, into the height of the soil prism perpendicular to direction of seepage flow, that is H cos I. So this pore water pressure U, this is the pressure. Please remember, this is the pressure, not the force. The pore water pressure U is equal to gamma W into H into cos I. It is acting vertically upward direction. Now on this surface CD, on the surface CD, this pore water pressure acting vertically upward direction. With this line CD, the pore water pressure here making the angle 90 minus I. In weight W, I explained that angle same as 90 minus I, because check this diagram here. Here the angle is I, this horizontal line and pore water pressure, this angle is 90 degrees. So this remaining angle is 90 minus I. So this pore water pressure with the line CD making the angle 90 minus I, we can resolve this pore water pressure U on the line CD. We can resolve this pore water pressure U into two components. One component perpendicular to line CD, other component parallel to line CD. So with this line CD, it is the failure surface CD. With this line CD, this pore water pressure making the angle 90 minus I. So on the line CD, we can resolve this pore water pressure into two components. One is a normal component. That normal component is the pore water pressure component. Next one is tangential component of this pore water pressure. Check those two components of the pore water pressure on the line CD. So on the line CD, this is the pore water pressure U. This pore water pressure U on the line CD resolved into two components. One is normal component N, normal component. Other one is tangential component. So on the line CD, on this line CD, this perpendicular vertically upward pore water pressure resolved into two components. One component perpendicular to CD, other component parallel to CD. This perpendicular component is U cos I. This parallel component is U sin I. Just now we discussed in the weight condition W, this normal component of weight W. Just now we discussed this normal component of weight W, W cos I, same as this pore water pressure. Because with this line CD, the pore water pressure making the angle 90 minus I, this normal component of pore water pressure U cos I, tangential component of pore water pressure U sin I. Please check this. U cos I is the pore water pressure normal component. So this U cos I is the pressure, not the force. Check this U cos I normal pressure. This U cos I is acting on the surface CD. On the surface CD, this U cos I, this is the pressure acting on the surface CD, normal pressure. From this pressure U cos I, we can calculate the force. that is called pore water pressure force normal to this surface CD. This is pressure. U cos I is the pressure. Convert this pressure into force. Force is equal to pressure into area. Since this U cos I is acting on the surface CD, convert this force pressure U cos I into force by multiplying this pressure U cos I with this area of the surface CD. Area of surface CD is width B. This is the width of that surface CD B into thickness is 1. So first convert this U cos I pressure into force, that is U cos I into B into 1. We know U is the pore water pressure. Already we calculated that magnitude. U is equal to gamma W into H cos I. So this normal pore water pressure, this normal pore water pressure is U cos I, that is U gamma W into H cos I into cos I. So this pore water pressure, this normal pore water pressure is gamma W into H into cos square I. Convert that normal pore water pressure into force by multiplying this normal pore water pressure with the area of surface CD B into 1. So check this calculation carefully. First we calculate this pore water pressure U. This pore water pressure U is equal to gamma W into H cos I. This pore water pressure U acting vertically upward direction on the surface CD. We resolve that pore water pressure U into two components. One is normal component U cos I. Next one is tangential component U sin I. The normal component U cos I, U value is this one, gamma W into cos I. This is pore water pressure U. We resolve that pore water pressure into normal component and tangential component. The normal component is equal to U cos I. This is the normal component of pore water pressure, not the force. That is equal to U cos I. U value gamma W into H cos I into cos I. So this normal component of pore water pressure is equal to gamma W H into cos square I. This normal component is acting on the surface CD. Area of the surface CD B into 1. So convert this normal component into force, because this normal component is the pressure. Convert this normal component into force. Force is equal to pressure into area. What is that pressure? Gamma W H into cos square I. What is the area? B into 1. So we are converting this normal component of pore water pressure into force, that is called the pore water force. So the pore water force on the surface CD in the perpendicular direction. So the pore water force capital U on the surface CD in the perpendicular direction is this pore water pressure gamma W H into cos square I into area of the surface CD B into 1. You will get the pore water pressure U on the surface CD in the perpendicularly upward direction gamma W H B into cos square I. We converted this pore water pressure into force. Force is equal to pressure into area. So this U is gamma W H B into cos square I. Now check this prism, soil prism. In the steady seepage flow condition, first we calculate the weight of this soil prism. We resolve that weight into two components on the surface CD. One is the normal component. This is the force, normal force. Next one is the tangential component. This is the tangential force. These two are the components of weight of the soil prism. Weight is a force, gravitational force. So N is the normal force, T is the tangential force. N is acting in downward direction. Then we calculated the pore water pressure on the surface CD small u, gamma W into H cos I. We resolve the pore water pressure into two components. The normal component is U cos I, that is equal to gamma W into H cos square I. we convert that normal component of pore water pressure into pore water force U. This is that force U from the pore water pressure normal component. We calculate this pore water force by using the normal component of pore water pressure. We know that this U is force, not the pressure, because U is equal to U cos I into B into 1. That is, we convert that normal component of pore water pressure into this pore water force U. Now check these two forces. At this base of the soil prism, these two forces are in perpendicular direction, but they are in opposite directions. These two forces are perpendicular to surface CD, but they are acting in opposite direction. N is called the total normal force. U is called the pore water force. So here the soil prism subjected to the total normal force N, the pore water force U, and also the tangential force T, and also the shear strength of soil S, preventing the failure. Now use these two forces carefully. One is the total normal force, next one is the pore water force. The effective force of this soil prism, effective force indicated as N dash. The effective force on this soil prism is equal to total normal force minus pore water force N minus U. N minus U is called the effective force on this soil prism. So we are going to discuss the stability of this soil slope in the steady seepage condition by considering total normal force N, the pore water force U, and also tangential force T, and by taking the shear strength of soil S. So check that calculation of factor of safety in the third case carefully. So this is the effective force in the soil prism N dash. The effective normal force is equal to total normal force N minus the pore water pressure force U. Total normal force N is equal to gamma saturation HB into cos square I. This is from the weight of the soil prism, and this pore water pressure U from the pore water. This is pore water force U. From the pore water pressure small u, we calculate this pore water pressure for pore water force capital U, that is equal to gamma W HB into cos square I. Then in this equation, take this HB cos square I common. So this equation becomes as gamma saturation minus gamma W into H into B cos square I. This is the effective normal stress, normal force N dash. By using this effective normal force N dash, we can calculate the effective stress sigma dash. Effective stress sigma dash is equal to effective normal force N dash divided by area of the surface CD B into 1. This effective normal force N dash is equal to gamma dash, because gamma saturation minus gamma W is called the submerged unit weight gamma dash. So it is gamma dash HB into cos square I divided by B into 1. So you will get this effective stress sigma dash is equal to gamma dash H into cos square I. Because of the tangential component T, the shear stress developing in the side slope, that shear stress causing the failure. So this shear stress tau is equal to tangential component T divided by area of the surface CD B into 1. Tangential component is gamma saturation HB cos I into sin I divided by B into 1. So this shear stress tau is equal to gamma saturation H into cos I into sin I. Now by using this effective stress sigma dash, by applying the Terzaghi equation or the Coulomb equation, we can calculate the shear strength S in the side slope. The shear strength S is equal to sigma dash tan phi dash. This is the Coulomb equation. Soil is cohesionless soil. Since the soil is cohesionless soil, the cohesion C equal to 0. Since the soil is cohesionless soil, the cohesion C equal to 0. So the shear strength S is equal to
కూర కలిసారు అది కదా బరువు అతనికి అది కాదు మామూలుగా ఇంతకు ముందు కూడా వాస్తారా
so in this cohesionless soil, the cohesion C equal to 0. So the shear strength S is equal to sigma dash tan phi. In this seepage flow condition, that sigma dash is equal to gamma dash into H into cos square I. So the shear strength in this seepage flow condition is gamma dash H cos square I into tan phi dash. Now calculate the factor of safety of shear strength in the third condition. Fs is equal to shear strength preventing the failure divided by shear stress tau causing the failure. The shear strength S resisting the failure is gamma dash H cos square I into tan phi dash, and the shear stress tau causing the failure is gamma saturation H into cos I into sin I. Cancel this H in the numerator and denominator. Cancel one cos I in the numerator denominator. Bring this cos I to the denominator. In this seepage flow condition, you will get the equation of factor of safety. Fs is equal to gamma dash by gamma saturation tan phi dash by tan I. This is the equation of factor of safety in the seepage flow condition for the infinite cohesionless soil slope. So in the seepage flow condition, the factor of safety of shear strength Fs is equal to gamma dash and phi dash. Gamma dash tan phi dash divided by into tan I. That is the factor of safety of shear strength in the seepage flow condition. Check that factor of safety in the seepage flow condition. We discussed the factor of safety in the dry condition. Fs is equal to tan phi dash by tan I. That is the factor of safety in dry condition. In the submerged condition also, factor of safety Fs is equal to tan phi dash by tan I. Whereas in the seepage flow condition, factor of safety Fs is equal to gamma dash, that is the submerged unit weight of soil, into tan phi dash divided by gamma saturation into tan I. In soils, this gamma dash is always less than gamma saturation. Normally gamma dash is half of gamma saturation. So the factor of safety in the seepage flow condition, check this equation carefully. If I take gamma dash as half of gamma saturation, the factor of safety in the seepage flow condition half of 1 by 2 into tan phi dash by tan I. In the dry condition, it is tan phi dash by tan I. In the submerged condition, factor of safety tan phi dash by tan I. Whereas in the steady seepage flow condition, factor of safety is half of tan phi dash by tan I. That is, if the soil slope is in seepage flow condition, that happens in rainy season. During the rainy season, the water is moving in the soil slope. If that water is moving in the soil slope, the factor of safety of soil slope reduces by half of the factor of safety in dry condition. So in the summer season, soil slope is having high factor of safety. In the rainy season, due to that seepage flow, the factor of safety of soil slope reduces by half of the summer value. So in the rainy season, due to that flow of water in the soil slope, the factor of safety decreases by half of the value. The soil slopes are subjected to failure in the rainy seasons more frequently, that you can understand from this equation. Here, this gamma dash is less than this gamma saturation. So the factor of safety in steady seepage flow condition is less than the factor of safety in dry condition and the factor of safety in submerged condition. Due to that, the soil slopes are subjected to failure in the rainy season because of this decrease in the factor of safety of the soil slope. So this is the reason why those soil slopes are subjected to failure in the rainy season, because of decrease in the factor of safety of the soil slope due to the seepage flow condition. So this is the discussion of stability analysis of infinite portionless side slope in the dry condition, in the submerged condition, and also in the seepage flow condition. So with this, the stability analysis of infinite portionless side slope is completed. Then we are going to discuss in this unit 2 the next concept, stability analysis of an infinite cohesive side slope. Just we completed the portionless infinite side slope. Next we are going to discuss the stability analysis of an infinite cohesive side slope. The difference is in the portionless side slope, cohesion C equal to 0, whereas in cohesive side slope, cohesion C is not equal to 0. We must also consider the cohesion C in the cohesive side slope. Now we are going to discuss the stability analysis of the infinite cohesive side slope. Here also we are going to discuss the three conditions: the soil in dry condition, soil in submerged condition, soil in seepage flow condition. For all those three conditions, we are going to discuss the derivation of factor of safety of this infinite cohesive soil slope. So please everyone follow this stability analysis of the infinite cohesive soil slope. Now coming to this discussion, in this infinite cohesive soil slope stability analysis, again you will consider the three conditions, that is a dry condition, submerged condition, and steady seepage flow condition. Since here the soil is cohesive soil, according to Terzaghi equation, the shear strength of soil resisting the failure S is equal to C plus sigma dash tan phi dash. In the previous case, the soil is cohesionless soil, so this cohesion C equal to 0. Whereas in this case, the soil is a cohesive soil. Since the soil is cohesive soil, the soil is having the property of cohesion. Attraction between the soil particles is called cohesion. So the shear strength of soil in cohesive soil is given by S is equal to C plus sigma dash tan phi dash. Sigma dash is the effective normal stress in the soil. Phi dash is the angle of shearing resistance of soil. C dash is the effective cohesion in the soil. So we are going to discuss the stability analysis of the cohesive infinite soil slope for the dry condition, for the submerged condition, and also for the steady seepage flow condition. Now coming to this discussion carefully, in this discussion we consider the soil slope as a cohesive soil slope. So this is the diagram. Please everyone follow this diagram. So here this AB is the infinite cohesive soil slope. It is a cohesive infinite soil slope. Let this infinite cohesive soil slope with horizontal making the angle I. We know that the infinite soil slope subjected to translational failure along the failure surface CD. In the translational failure, the failure surface CD parallel to the surface soil slope AB. So with horizontal, this failure surface CD also making the angle I. Let H is the vertical height between the infinite cohesive soil slope AB and the failure surface CD. Then in this discussion also, we are going to consider the soil prism between the soil slope AB and the failure surface CD. Same as the previous discussion with slight modifications. So go through this concept carefully. This is the stability analysis of infinite cohesive soil slope. So take that soil prism between the soil slope AB and the failure surface CD. You know that B is the inclined width, H is the vertical height. The area of this soil prism, first calculate this horizontal width V cos I, vertical height is H. So the area of this soil prism is H into V cos I. Let W is the weight of this soil in the dry condition. Since it is in dry condition, we must consider the bulk unit weight of soil gamma. Take the thickness of this soil prism in the perpendicular direction as unit thickness. So the volume of this soil prism is H into B cos I into 1. Take gamma is the bulk unit weight of the soil in the dry condition. So this weight W of the soil prism is the unit weight gamma into volume HB into cos I. This gamma is the unit weight of soil because the soil is in dry condition. The weight W acting vertically downward direction on the surface CD. Resolve this weight W into two components: normal component N, tangential component T. Normal component N is W cos sin I, tangential component T is W cos I. This entire discussion is same as the earlier, but I will tell you the modifications in this cohesive soil slope at the end. So this weight W is resolved into two components: normal component N perpendicular to surface CD, tangential component T parallel to surface CD. The normal component N W cos I, that is equal to gamma HB into cos square I. The tangential component T is equal to W sin I gamma HB cos I into sin I. Now check this soil prism in the dry condition. Here the soil is cohesive soil, not the cohesionless soil. The normal component N produces the normal stress in the soil prism sigma. This is called the total normal stress in the soil prism. That total normal stress is equal to normal component N divided by area of this plane CD. The area of the plane CD B into 1. The tangential component T produces the shear stress tau in the soil. That shear stress tau is equal to tangential component T divided by area of this base B into 1. This shear stress is acting in downward direction. This shear stress causes the failure of this entire soil mass. So this is the shear stress causing the failure. Whereas this soil, cohesive soil, is having the shear strength, internal shear strength S. You can calculate the shear strength S by using the Coulomb equation or Terzaghi equation. In cohesive soils, S is equal to C plus sigma dash tan phi dash. So calculate that normal stress sigma, normal component by area N by B into 1, that is gamma H into cos square I. Then the tangential component T produces the shear stress tau T by B into 1, that is gamma H into cos I into sin I. This shear stress tau causing the failure of the soil in that infinite cohesive soil slope. Then since it is in dry condition, the soil is in dry condition, there is no pore water pressure in the soil. In the dry condition, there is no seepage flow, so there is no pore water pressure in the soil. So the pore water force U, capital U, is 0. Since that pore water pressure is 0, the effective stress, the effective normal stress sigma dash is equal to total normal stress minus the pore water pressure. In the dry condition, pore water pressure is 0, so the effective normal stress sigma dash is equal to the total normal stress sigma. So apply the Terzaghi equation to calculate the shear strength of soil resisting the failure. S is equal to C dash cohesion plus sigma dash into tan phi dash. This sigma dash is equal to sigma. We calculate this total stress. Sigma is equal to gamma H into cos square I. So calculate the shear strength S in the cohesive soil, preventing the failure of the soil slope. It is C dash cohesion of soil plus gamma H cos square I into tan phi dash. This S is the shear strength preventing the failure of the soil slope. Tau is the shear stress causing the failure of soil slope. Now find out the factor of safety in the dry condition for the infinite cohesive soil slope. Fs is equal to the resisting shear strength by shear strength causing the failure S by D. S is equal to C dash plus gamma H cos square I tan phi dash divided by tau is equal to gamma H cos I into sin I. Take that as equation 4. This is the equation of factor of safety for the infinite cohesive soil slope in the dry condition. In this equation, this phi dash is the angle of shearing resistance of soil. I is the angle of soil slope with horizontal. C is the portion of soil. So by using this equation 4, we can calculate the factor of safety of the infinite cohesive soil slope in the dry condition. Now in this infinite cohesive soil slope, we have two more conditions: submerged condition and seepage flow condition. Next class, I will explain those two conditions in this infinite cohesive soil slope. Dear students, if anybody is having doubts regarding this discussion of infinite cohesionless soil slope and also the infinite cohesive soil slope, please ask me. If anybody is having doubts in this stability analysis of infinite cohesive soil slope and also infinite cohesionless soil slope, we completed already the infinite cohesionless soil slope in the dry condition, submerged condition, and also seepage flow condition. Just now we completed the infinite cohesive soil slope in dry condition. If you have doubts in this discussion, please ask me. Any doubts, students, regarding this discussion of infinite cohesive soil slope stability analysis and it is infinite cohesive soil slope stability analysis? If anybody is having doubts, please ask me. Okay, students, if I am not having the doubts, I will stop the today's class. We will continue this discussion, the stability analysis of infinite cohesive soil slope, in the tomorrow class. So with this, I am going to stop the today's class. We will continue this discussion in tomorrow class.